Earlier today we had a look at Higgs branching ratios in the standard model. So I told you, where's the nice laser pointer?
It's been stolen by the elves.
Stolen. Been stolen by him.
And he's an elf, clearly.
Thanks, man. All right, and just by looking at the number of lines that really intersect here, you can see that 125 GeV Higgs really allows us to obtain, probably in the future, a quite fine-grained picture of the dynamics of the Higgs sector and its relation with the fermions and the gauge bosons as well. So Higgs width, total Higgs width doesn't matter. We had a look at all the production mechanisms. So gluon fusion is the biggest one at 13 and 14 TeV, actually also at 8 TeV. And followed by weak boson fusion with its funny kinematical quirks and small uncertainties and higher order corrections. Then associated production with W's and Z's, and I particularly said a few words about ZH production and how it relates to this substructure revolution that came about 10 years ago. And TTH as probably the most complicated process at the LHC. And this is why this is lacking a little bit behind in terms of sensitivity. Okay, so now I want to focus a little bit on new physics possibilities and opportunities that provide themselves through the Higgs mechanism and through the Higgs boson interactions in particular. So, of course, you all know there is a plethora of models out there with resonant extensions, but at the moment it seems like that nature is not that nice to us. So what I'm going to focus on is mostly deviations of the Higgs coupling patterns and how we can sort of pin them down at the LHC in the future, and what other precision measurement environments, let that be a 100 TeV collider or a high precision lepton collider environment. What can we actually learn from Higgs data, and what will be our best guess on the basis of that outcome? That's what I want to talk about today now. Okay, so this is what I showed you earlier. So this is pretty much where we are at the moment. So this is the Atlas CMS run one combination, so they combined their data sets. So it's only not really the latest result, so it is from 2016, but not really much has changed since, okay? I mean, these error bars will go down slightly. So we see a nice pattern that shows that actually in this kappa framework, which is essentially you take coupling, for example, what do we have here? Kappa W. Kappa W is you take the coupling of the Higgs to two W's, and you subtract it, you divide it by its standard model expectation. Okay? And then you let that float freely, and if stuff is consistent with one, then pretty much the standard model is bang on. And this is the situation that we see ourselves in. Okay? There are two sets of fits here. So one assumes a zero beyond the standard model contribution to Higgs decays, and another one assumes that actually there is a new contribution to the Higgs width that could come about in this singlet scenario, where the Higgs decays into two extra scalars, could be related to dark matter, blah, blah, blah. So you can see that this can be still quite large, okay, because we're early in the LHC program. And an additional assumption, or two additional assumptions here, is that we take these couplings to be smaller than one, which means that we break electroweak symmetry with a doublet, not with a triplet, and blank out the negative Yukawa sign here, okay? So this is done by hand, if you wish. So this is what Atlas and CMS have provided us. Of course, the theory community is not sleeping, and they run their own fits. So Tillman and his group in Heidelberg are doing a lot of work in that direction. And because this kappa framework, okay, so imagine again that you deal with WW scattering, and I change the size of this coupling, I will induce all sorts of problems in the high energy limit, okay? So I said earlier that WBF is not very responsive to these deviations and so on and so forth, but just changing couplings breaks electroweak gauge invariance, and it breaks it in a bad way. And this is what we try to avoid, because the more data we have, the more we would like to study differential distributions, as well I'm going to talk about today as well, the more relevant gauge cancellations will become. So it's only natural that you go to a framework that is not just toying around with couplings like this in a rather naive way, but extends the standard model interactions by interactions that are consistent with gauge invariance. Okay, and this is in a nutshell what these O's here for gauge invariant operators really mean. Okay, at the same time, you can see that these constraints are still rather loose. So whatever coupling constraint that you have here, so you could call this a Wilson coefficient. If you translate this into a scale by making an assumption that this coupling is of order 1 or something, then you can see that actually we are dealing here with scales that are of the order of the electroweak VEF. Okay, so at the moment we are not really very sensitive to high-scale physics at the LHC. And the hope is the more data comes in, we'll be able to look into more exclusive phase-space regions that pin down these new interactions more precisely, and also resolve some of the blind directions where these things just pull in different directions, and you have cancellations between new couplings and new physics. Yep.
Just missed an explanation or something. Why are there multiple vertical levels? So like there's standard model expectation value 68% is this red. So, but there's 3 reds that are non-overlapping vertically.
3 reds that are non-overlapping vertically. So you mean that one, and that one.
Well, what is the difference between these
You have multiple minima in the coupling fit.
Okay.
So strictly speaking, this framework will only be allowed around here, because these minima are not really like perturbative deviations from the standard model. But it's a reflection that we don't really have enough data at this stage. All right, so let's talk a little bit about this dimension 6 business. So I want to show you how this also relates to the traditional problems that we have in the Higgs sector, like the hierarchy problem, for instance. So we had the S parameter, and the S parameter actually constrains one operator direction that mixes the W fields with the B fields. So typically you write down these operators in the unbroken phase. And that looks like this: H dagger TA, H W A mu nu, B mu nu. So this direction is constrained under the assumption that the fermions couple to gauge bosons as they do. The T parameter is related to an operator there is called OH, and that's H dagger covariant derivative H squared. Okay. So these operators we already studied, in the context of electroweak precision observables. So already know that some of these operators, just by studying the stuff that we already knew before the LHC turned on and discovered the Higgs, are already constrained from precision measurements. So after the Higgs discovery, everything changes, of course. So, and in principle, you can extend this set that was just mapping out correlations of 2-point functions, if you wish, and apply the same strategy to the Higgs itself. Okay, so you can play identical tricks in the Higgs sector. So for instance, you look at 2-point functions of the Higgs. The Higgs has a self-coupling. It couples to W bosons, of course. And it couples to the top quark. Okay. So this is one class of diagrams, and another one is you take this guy. Has also trilinear vertex. Okay. And a vertex like this. So if you were to calculate these one-loop diagrams, you would see that they scale d4k divided by 2 pi to the power 4, 1 divided by p squared minus mh, k squared minus mh squared. And if you go to large Euclidean momenta and you regularize everything with a cutoff, then these loop integrals scale like lambda squared. Okay. So this is the origin of the famous Weltmann condition, namely that contributions to the mass renormalization, this is exactly what these A0 terms are, they feel they're quadratically sensitive to thresholds and employ, well, you have to, it's not a technical problem, but it tells you that there is a level of fine-tuning here involved, which can be technically solved just by fixing the parameters as they are. So these contributions, they affect the mass, okay? But we're doing perturbative quantum field theory, so the mass is not a parameter. The mass is now fixed because we know it's 125 GeV and we have to live with that. So that's input data. But this diagram, together with these two, they also contribute to the wave function renormalization of the Higgs. So this would be B0 functions instead of A0 functions. And the top, because it has this funny Dirac structure, just contributes an A0 function as well as a B0 function. So if you do that, then just by the ordinary rules of renormalization, you shift the standard model by some contribution, ZH, that's renormalized but has finite remainders, d mu h squared. And now we would like to work with a canonically normalized field, so we have to absorb this into a redefinition of the Higgs field. This is what you always do. And let me just sneak in one additional term here. MT, TT bar, H for instance. So we absorb this stuff now into a redefinition of the Higgs field strength. And what we find then is that all Higgs couplings are, well, this is essentially included here in that term, okay? So the standard model after canonical normalization contains now TT bar 1 minus delta ZH times H coupling. So the claim here is that whatever new physics pops in here, okay, and supersymmetry is one particular example where you have the Higgs CNO mending the quadratic divergence from here. You have the Wieners and the stops, each pairwise saturating this quadratic divergences. But these couplings here, they are gauge related, okay? So this means that whatever new physics pops in and sort of removes this sensitivity in the Weltmann condition should also show its face in the wave function renormalization, and as a consequence in a uniform rescaling of the Higgs coupling pattern. So this means you can have actually something like a precision measurement of the Weltmann condition itself or of whatever mechanism that drives a solution to the hierarchy problem. And the relevant operator for this in the language here of dimensions, higher dimensional operators, is this guy, d mu h dagger h, d mu h dagger h, okay, which is dimension 6, okay, and that's good because that means it's a dominant deformation of the standard model. If that was dimension 8, then we would be a bit shafted, but we're not. Okay, so in principle this works, and if you now compare this needs high precision Higgs coupling extractions, okay, and a hadron machine is not really super suited to that. So if that is really the only impact that you get from high scale physics, which would be unlikely, but if let's imagine that's the case, then a 240 GeV, 250 GeV linear collider can in principle measure Higgs couplings at the percent, sub-percent level if they are uniformly rescaled. So this you could actually, so you could in a way test fine-tuning at the 10% level just by looking at precision Higgs coupling measurements. And so these are just a handful of operators. Unfortunately, there are more. There are a lot more. And Tim is probably going to talk about that in a lot more detail. But just for completeness here, what we do is we extend the standard model by all dimension 6 operators that are gauge invariant and consistent with the symmetry requirements of the standard model. Okay, so you would have the Wilson coefficient divided by some scale and some new operator OI. And if we buy into barrier number conservation, which is probably a good thing to do, then there are 59 operators times flavor structures times permission conjugation. And that means there are 2,499 of these new interactions. Okay, so we have 2,499 parameters. Yeah, it's just looking at Susie in the rear mirror. Okay, so that's quite bad. And it comes at the additional assumption that whatever scale sits here is not kinematically resolved at the LHC, right? So there are no particle thresholds, no resonances, nothing. Okay, so it's rather pessimistic outlook as well. Most of these couplings arise in the 4 fermion sector. So you have like a lot of flavor changing currents and 4 fermion operators and blah, blah, blah. And there's only really a handful that are relevant in the Higgs sector, okay? So the Higgs sector provides a very good sort of approach to measuring these things really at the LHC, and this is also what Tillman and his collaborators have done there. So let me go through a few concepts how you measure these things, okay? So in flavor physics, this is completely abundant. Yeah? So people who've done flavor physics, maybe some of you do flavor physics, for those this is really old news. Yeah? You deal with scale separated physics, you integrate out your ultraviolet degrees of freedom, and you match it onto some effective interaction, and you constrain whatever low energy constants that you are left with. Even the mass hierarchies that we're dealing here with are pretty much the same as flavor physics. Okay, so for example, you take the B mass divided by the W mass. This is something like 20. Okay, so this is the typical mass scales that flavor physicists worry about if you, for example, want to study B decays. That is a weak process. The W mass is a relevant scale for that, but you do the measurement at the bottom mass, so you deal with a hierarchy of 20. If you apply the same 20 to the vacuum expectation value, which would be our reference scale, if we do a measurement at the electroweak scale, you end up somewhere in the 5 TeV regime. And that is typically the mass scale where people say, okay, this is where new physics should sit. Yeah. So either stops or extra dimensions and that sort of stuff, and row-like states that show up in compositic scenarios and so on and so forth. So 5 TeV is a good and realistic mass scale that you can probe directly at the LHC. Okay. So in principle, this means that EFT methods should work, because at 5 TeV, center of mass energy, partonic center of mass energy, the LHC runs out of steam. So for most processes that are really relevant for Higgs, even lower than that. All right, so yeah? Yeah, the tadpoles you can just renormalize away into the sources. Yeah. I mean, the way that this is not ultraviolet renormalization, but it's a finite one that you compare against the standard model. So yeah, but tadpoles, of course, it's just the motivation, right? I mean, you chose them to be 0. You can't do that. Yeah, so this would be the yeah, absolutely. Yeah.
That kind of term, like kinetic term of Higgs is
Yeah, I mean, yes, of course, it's a dimension 6 operator, so it had, so that I'm not really sure if this is the question you're asking. So it's dimension 6 operator, so it has to come with a lambda squared here. And when you expand this operator around its VEF, then it contributes exactly to a shift like that. Yeah. But this is true in general, so whatever kind of new stuff I throw into the loops here will show up as a finite correction of Higgs couplings in the entire renormalization procedure. Yeah. Yeah, yeah. Yeah, so but this is finite renormalization, so there's no infinities attached to that. Of course, if you throw in a realistic model, you can do this in the MSSM, then you can renormalize everything, but you see exactly these effects, okay? But you see more of them. And you know what I said here is that this is the only source of new physics, yeah? Which doesn't really make sense. So you can do this in the singlet scenario, where the Higgs, you know, but then of course you see stuff in the W sector as well and so on and so forth. Yeah? So it's just an approximation, like the ST and U parameters are an approximation to the full thing. Now you have one additional degree of freedom that you can study along these lines. So when I say that this is similar to flavor physics, then I'm actually lying, yeah? Because flavor physics is a very, very well-defined process in terms of measurement, okay? The bottom quark sits there in a B meson. You have nice factorization theorems, the BBNS formula, and so on and so forth. But the LHC is quite a beast, so it will actually marginalize over all intermediate energy scales that are there. So you integrate out your W boson, and the B meson sits there and then decays, so there is a clear separation between scales. Here at the LHC, you probe 5 TeV through kinematic distributions, okay? So there is an added complexity due to this. Okay, so, but that also presents itself as a massive opportunity, right? Because a lot of these operators here, and we had a look at the H dagger Hg squared, they have momentum dependencies. And these momentum dependencies are enhanced when we go to high invariant masses, okay? So if you study the phase-based dependence of these new interactions, we can actually get a fine-grained picture of what's going on. Okay, so this presents both limitations but also opportunities. So let's go back to this example of H2 glue, which is a good example to have a look at. So we saw that this diagram here leads to an operator at dimension 6 level that looks like this: H dagger H and a G A mu nu G A mu nu. Actually, because it's because these couplings are related to Higgs VEF insertions, you can resum this entire chain of operators into a logarithm, and that goes under this famous low energy effective theorem in Higgs physics. There's a very nice paper by Michael Spierer and Bernd Kniel, so if you're interested in that, have a look. It's really nice. So, and we saw that even for MT to infinity, we don't get decoupling. Okay, so this operator will be there, irrespective of the mass scale that runs in the loop. So, what does this mean in practice is, let's not look at this operator in isolation, but also add one that shifts the top Yukawa coupling, okay? So, that's also present at dimension 6 level. So, if you have an additional operator here that looks like this, CT, so CG, CT minus plus, okay, H TT bar, then we really vary. So if we send this guy to infinity, then what happens is that we deal with a point-like interaction, okay, with a different Lorentz structure and a different momentum dependence. But now we also shift this coupling away. And unfortunately, these two things, can compensate each other. and because they have at low momenta, you can't really tell a difference between these two so much. Yeah? You really have a blind direction. So if I, for instance, normalize this guy here to gs squared and 16 pi squared v, and I look at this guy and I send m top to infinity, I get a minus square root of 2, 3 ct by yt times og. Okay, so I start with a modification of the top sector, but if the top mass was infinite, then it leads to a degenerate structure with this operator as well. Okay, yeah. Yep, yep. Yep. Oh God, not much. In essence, this would correspond to the doublet, but because that doesn't really work out with dimensions, let's do it like that. Okay. So in essence, these two guys here, if the top mass goes to infinity, there is a blind direction that looks like Cg minus square root of 2 divided by 3 Ct equals to 0, okay? Because Yt is roughly 1. So unfortunately, the effective interaction for Mt goes to infinity is quite a good one, yeah, for inclusive rates. So we saw this because people are using this to calculate higher higher order corrections. So if we're only interested really in the total gluon fusion production rate, then we'll be sensitive to exactly this this degeneracy, which means that we measure a standard model-like rate, but it could be Ct compensating Cg with an additional prefactor, which is essentially just normalization. Okay? So that's bad, and we have to work to make this better. So the difference here is really that we have to look into phase-space regions where this degeneracy gets broken, or we add new processes that are individually sensitive to these new interactions. That could be Tt bar Higgs. Okay, so Tt bar Higgs is a has the top Yukawa coupling here, but of course you could also include insertions like this. Now we have a coupling of the Higgs to the gauge boson field, so we could also radiate it off from the initial state. But numerically, it turns out that these contributions are highly suppressed compared to that. So adding Tt bar Higgs production to this game certainly helps, okay? Because then you measure this, and then you measure the sum, and you can constrain both parameters. But what I want to show you is actually you can also just use the power of the LHC to resolve the top loop. So we had that this guy here has contained a Z0 function, mh squared, mh and m top. Okay, and if you produce it, then this mh can be replaced by the center of mass energy. So if that goes bigger than m top, something will happen. Okay. Yeah, because you start becoming sensitive to the top threshold, and we can see this in the production mode as well, right? So you see that you get these enhancements, and of course these enhancements sort of manifest themselves in deviations of the Higgs PT spectrum as well. So if we were to look into the differential cross-section of Higgs production in this particular channel as a function of its transverse momentum, then what you get is always a logarithmic on a logarithmic scale, something like a linear drop-off, okay, until it runs out of steam, PT Higgs. The effective interaction we saw comes about by essentially removing the m-top dependence and sending this to infinity, okay? So at no point in time can you actually have a square root of s which is bigger than mt, okay? So roughly above to, roughly around mt, kmpt, you will see a deviation, and depending on the sign of CG here, I get an enhancement or I get a smaller contribution, which would be proportional to minus CG. Okay. On the other hand, if I modify my top-Yukawa coupling, then I just shift this distribution up and down, but I don't change its shape. Okay, so this would be something like CT. Okay, or I can shift it down. So this means now I can really study the PTX spectrum and compare it against the standard model. And even if the inclusive rate, which of course the cross-section, the differential cross-section here is largest for small pt because everything drops exponentially, even if they intersect there and everything looks standard model-like, still I can get this massive deviations in the tails if this is not, even if it sits on the blind direction, okay? Because this really induces a different shape than CG, okay? That's the idea of it. However, the problem here is that we can't really access stuff like this. So what you can do, so I mean here the PT of the Higgs would at leading order be exactly 0, right? So you have an incoming quark has no PT, you have an incoming gluon, you have an incoming gluon from the other side, both have no PT, so there is no PT. In order to get PT, we have to radiate off some gluons, and we can do this either here or here in the loop, okay? So what we really want to do is look at, diagrams like this and diagrams like this. Okay, so you have initial state radiation, but also if you produce this really at high PT, it starts resolving the substructure of the Higgs interactions with gluons. So it's a little bit like the Rutherford scattering cross-section, right? So you whack gold atoms with high enough energy. Once your momentum transfer becomes comparable to the Compton wavelength of whatever subsystem that you're studying here, you should see quantum mechanical effects appearing, and those will be related to whatever mass scale could potentially be there. Okay, so this is a little bit how you can influence and extract new physics information from differential distributions. So, of course, there's a slight catch here. Namely, we have to limit ourselves to a region of Wilson coefficient numbers, okay, so values of CG, which makes sense somehow. So the unfortunate truth is that we have to rely on Monte Carlo simulations and perturbation theory as a consequence to realistically model final states at the LHC. There's no way that you can put this into a lattice calculation and calculate the W plus 2 jet rate. So we're not there yet, okay? So we have to use perturbation theory, and that perturbation theory will have limitations, okay? Because now we add a whole lot of new parameters to it. So as a side note on validity, we can look again at the Lagrangian that we split up into the standard model plus dimension 6 pieces. Okay, we can do the necessary field redefinitions and so on and so forth and end up with a set of of new parameters, and then calculate the matrix element, and we can split it up exactly like this just by bookkeeping inverse lambda squareds, if you like. Okay? So you do this now with M, you have a standard model amplitude piece, and you have a dimension 6 amplitude piece that's suppressed by lambda squared. So in order to calculate the cross section, you have to take the modulus squared of the amplitude. You get a m squared is m standard model squared plus 2 times the real part of the interference of the standard model, complex conjugate, with the dimension 6 piece that's suppressed by lambda squared. And a dimension 6 squared piece divided by lambda squared. Okay. Times 4. Okay. So already here you can see that this truncation at the dimension 6 level, which we're implicitly assuming, can cause trouble, because this dimension 6 squared term is formally dimension 8. And if I were to write dimension 8 pieces into my Lagrangian, I could interfere the dimension 8 piece with the standard model. I would get a contribution that's exactly the same order. But I don't include these. So formally, to stay at the dimension 6 level, you better had only look at the interference part. Now, we deal with 2,499 interactions. There are accidental cancellations. Okay. So, for example, if the new interaction produces new helicity rules or new helicity combinations that you can't interfere with the standard model, or they are chirally suppressed proportional to the charm quark mass or something like that, right? Then there is no good solution to that, but you can look at these operators then individually and study them at the squared level. But there is a nice relation of this to higher order corrections as well, because it gives you something like a technical validity range at which this whole mechanism of event simulation and stuff breaks down. Okay? Because if I throw this piece away and only look at the interference part, then this m square is not necessarily positive definite anymore. Okay? And it becomes negative exactly when this piece outperforms that guy. Yeah? And because some of these 6 parts are enhanced at large PT or at large energies, this typically happens in the tails of the distributions. So one way of gauging a maximum value of the Wilson coefficient at a given lambda squared is that you require that these distributions are positive definite integrated over bin sizes. Okay? So that essentially these curves, the dashed curves, always stay positive and never go negative. And because we linearize everything, this also gives you you just flip the sign of this critical Wilson coefficient, you also get a limit on overproduction, because everything is just linearized in the tails. So you get a solution with a nice feature, all right? So that causes issues in setting these constraints. And coming back to this plot here, you can see that these double triple minima in inclusive rates, they will typically go through a range where you dip with the cross section, but then the squared piece becomes important and sort of shoots you back into the positive definite part. Okay, and so if you were to linearize everything, then these guys would be away, because you would have to reject that region of Wilson coefficient just to make sure that you are close to the standard model where you can trust your perturbative series expansion. Okay? And that will become, that's at the moment is not super important, because we have almost no information about the differential Higgs spectrum. So there are only a handful of analysis out there. But of course, with the lifetime target of the LHC of 3 inverse Autobahn, we will have the Higgs PT spectrum nailed down quite precisely. And then you have to start worrying about these effects. All right. So are there any questions related to that? This here.
Yeah.
So
Like in the OB, you don't get, you get only the Gluon term and the fermion term.
yeah, so what we did that calculation, right? So we have. Do I have it here anymore? Yeah, I mean, previous lecture we had the exact form here of C naught. So we had written it down. I just can't. I mean, so what you do is essentially you integrate out the top mass. You calculate the full thing, yeah, using this is just a new Yukawa coupling contribution, if you wish, at fixed top mass. You calculate this guy and send m top to infinity. You get exactly this operator, yeah, and then you just match the coefficients. And you can do this. So the way this interaction works is that I don't really have the result by Spira in my brain, but you can just look at what is the effective h dagger h g squared operator that gets generated by infinite top masses, and you just compare it to this guy. And then you just match the coefficients, and you require that operator to be absent, and this gives you the blind direction. But that's only true really for inclusive rates. And as you see here, you can resolve this, hopefully, for large PTs. Yep.
Question. By sending, by integrate out the top, you actually keep the call remain the same.
Yeah.
And do you mean by send
No, you can't do this because then you decouple all masses. So this CT is not just the Yukawa coupling, but it's an additional contribution that is Yukawa-like, but does not change the top mass. Okay. Would be an operator like this. You have h dagger h, psi bar h psi, divided by v squared, for instance. So you fix the fermion mass, and then you shift everything into the interactions, and this manifests itself as a shift in the Yukawa interactions. Anything else? Dimension 5, only the neutrinos are relevant. There's only one operator. Dimension 7, many more operators. Yeah. Dimension 8, also more operators. Actually, people are working at the classification of that. So it took quite a while actually to find these 2,499 operators, believe it or not. Yeah. Because there's a whole load of redundancies, and you have to be really careful in not overcounting this. So the first few papers had gauge redundancies, had equations of motion not used, and it took 10, 15, 20 years to really settle this operator basis of 2,499 operators, which was actually the master thesis of a student. Really, really tough. And the first ones to do this were a bunch of people from Warsaw. And this is why this particular basis with the 2,499 operators is also referred to as the Warsaw basis. And it's a paper that just sat there, not collecting any citations, and now it's just skyrocketing. Yeah. It's like the Weinberg paper for the standard model itself. Maybe. Oh God, this is really mean. Oh God. I'll look it up in a minute, okay? But it's like names that are almost impossible to pronounce for me, with lots of Z's, and so I don't want to make a fool of myself, which I probably already have. So let me dig that out, and I can give you the archive number, which has not such a problem, okay? This is why people call it the Warsaw basis, yeah? All right. Okay. Oh, yeah, of course.
It's 1008-4884.
Okay. 1008 4884. So, can somebody look up the authors?
Any volunteers?
Mesonia, okay, that's a fairly, that's the most, pronounceable name probably. Doesn't matter, okay, let's crack on with it. Yeah, see, not that easy, huh? All right. So one thing that is crucial to this is getting the uncertainties right, of course, right? So we're assuming a slightly pessimistic situation where no new physics shows up, but at this point in time, probably not so unmotivated. Okay, so this will come with an associated uncertainty band that will typically go larger in the tails of distributions. So we want to make sure that we are not really missing anything there. And some of these, some of the effects that sort of make these uncertainties large or small, we can already absorb into a smart definition of these operators and a smart normalization. I want to just quickly go through that because it's what a lot of people worry about these days is radiative corrections to operators like this. Okay, so where do I have it? Oh, here. All right, so let's look in particular at this operator OG, which is H dagger H, GA mu nu, GA mu nu. And what we do is we extend the standard model by this particular operator, and we forget about this matching comparison that I just did. H dagger H, GA mu nu, GA mu nu. All right? So now the question is, can I systematically improve this using perturbation theory? And normally, this is what people like me have been taught in their undergrad degree classes, is that higher dimensional operators amount to non-renormalizable interactions, so you're screwed, okay? But that's not entirely true, okay? So at any given order of perturbation theory, you can renormalize this, okay? But you have to truncate at the dimension 6 level straight. Yeah, so you can do this in the MS bar scheme, which means that at this stage CG is not really a physical input, but it's just an MS bar renormalized parameter, or a renormalized parameter that has no renormalization scheme that has no physical interpretation. So let's calculate this, and I promise it's not going to be super hard, okay? And it tells you that that there is something that you can do to systematically improve uncertainties in these sorts of approaches. So the way this always works is that you interpret the parameters here in the Lagrangian as well as the fields as bare quantities, and then you introduce multiplicative renormalization factors. So this becomes an L0 for bare quantities. This gets a 0. 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 Yeah? Then we introduce these renormalization factors. So you end up with the standard model Lagrangian. There is now a function of renormalized fields and renormalization constants. So you have a renormalized gauge field, a renormalized Higgs field, and so on and so forth. And in this interaction, you have the renormalization constant related to a CG divided by lambda squared, and ZH times ZG times H dagger HR GA mu nu R GA mu nu. R. And we want to really work out that set C and then plug it into a renormalization group equation, right? So you all know that the strong coupling is running. And if you don't include that in your med event simulation, for instance, you get a result that's completely off. Yeah? And this RGE improvement that you do at leading order just resum some of the dominant corrections that you would expect from higher order corrections. So we treat CG really here as an analogous coupling that just relates to a dimension 6 operator. And this lambda squared term in the denominator, we just use that to bookkeep the formal series expansion of our Lagrangian, okay, and associated interactions, which means that we're really doing a double series expansion here. One in the couplings and one in inverse lambda squareds. So we see that for this stuff here, we need ZH, we need ZG, and then we need to calculate the one loop corrections to this vertex, and then we can infer ZC. Okay, let's do that. And this really ties the loop because all of these quantities are gauge dependent. And of course we need to make sure, we said this at the beginning of these lectures, that in the end this gauge fixing parameter should not show up in the physical result. And the RGE flow is a physical result, so we would not expect it to show up there, otherwise we've made a mistake. So in the first step, what we need here is the wave function renormalization for the Higgs. Okay, so you can get this from a 2-point function of the Higgs. And typically you do these calculations. I mean, we do this here in the unbroken phase. It's just a bit easier, okay? So you write everything down. You have your leading order propagator. Then you have this new interaction, okay? Gives rise to an A0 integral. So this will not impact the wave function renormalization. That's great. And you have terms like this, which are standard model-like, okay? Well, these are W's and Z's. So you get a plus extra terms, okay? I'm not writing down all of them. And I forget about the top for a second, okay? Because that just makes equations a bit more compact. So these guys, that's just my one. All of these will give me a contribution to my ZH, and all of these ZIs I can write as a 1 plus a delta ZI, yeah? And this is numerically, well, as a formula, minus 1 divided by 64 pi squared, 3g1 squared, plus a 9g squared, minus a g1. So g1 is the hypercharge coupling here, all right? So I slightly digress from my earlier notation here. G1 squared, you get the gauge fixing parameter related to the B fields, minus 3g squared, gauge fixing parameter for the W fields. And that carries an infinity, and you can write this as a delta bar, which is just the ms bar divergence in dimensional regularization. So it looks like this, 4 pi mu squared divided by m squared epsilon gamma 1 plus epsilon divided by epsilon, okay? So m is just an arbitrary reference mass scale. It will drop out of the final calculation. Okay, you can choose this as a W mass. This is typically what people do. So now we got this, grand. Now we have to calculate the Gluon renormalization constant. So we need delta ZG. And this we can get by looking at Feynman diagrams that are related to the Gluon two-point function. And I just give you the result. So delta Zg becomes a gs squared minus divided by 32 pi squared 5 minus 3 psi g. Okay? So we got these psi's floating around left, right, and center. And finally, we need to calculate the amputated, or we can also calculate the full 4-point function, but I want to calculate the amputated 4-point function that arises from an interaction like this, where the two Higgses are coupled to gluons. So you get something like that. Yep. And this goes into terms like this, where you have one operator insertion here. So the squared book keeps the 1 over lambda squareds. And then, of course, you can get terms where you connect the gluon lines. You can get higher dimensional contributions where you couple this into where you close the 6-point function like that. Okay. And so on and so forth. Okay. So it's quite a few of these. And you would call this just as by definition, as a CG0 times the matrix element, OG0. Okay. To start with, this would be that term. And now comes all the other stuff. And I also give you the result for that. Plus a CG0, OG0 times our delta bar divided by 64 pi squared, a G1 squared psi b, because we also have gauge loops in there, okay, plus a 3 6gs squared minus 8 lambda plus a 2gs squared psi g plus a g squared psi w. Okay. And you would call this delta Z4, for instance. Yeah? So these things are just for reference. So what I have here is that I have a CG 0, OG 0 times a 1 minus delta ZH minus a delta ZG plus a delta Z4. This is now renormalized, sorry. So I just shift all, I just express my amputated Green's function in terms of the renormalization constants and the renormalized amputated Green's functions. This is where the ZH and the ZG come from. And this has to be equal to a CG renormalized, OG renormalized 1 plus ZC. So calculating now the 4-point function, and with the ZHs and the ZGs, I can express now my my renormalization constant for ZG. So I could write CG naught as a CG R times, and I give you, I don't really quote the full result yet because that's really just not too important. So this is a 1 minus delta ZH minus delta ZG plus a delta Z4, and this would be just a 1 plus delta ZC. All right, so in this procedure, the right-hand side here has a mu dependence because everything is proportional to delta bar, and delta bar has a mu dependence, right? So in principle, this is a function of mu, and this is a function of mu, such that the bare quantity is not a function of mu. And from this you can now derive a RGE equation. So let's do that. So the bare quantity has no mu dependence, so if I take the logarithmic derivative of this parameter, I should get 0. And following a few steps here, you can write this as a, if you express this now in terms of this delta z and everything, this is a logarithmic type of thing, and you multiply the z. So in the end, this leads to a relation that is a renormalization group equation for the renormalized Wilson coefficient that reads as a minus d delta zc divided by the logarithm of mu times cg renormalized, okay? So with all these field strength renormalizations, you can calculate delta zc. Then you take the logarithmic derivative of this guy, send epsilon to 0, and there you have your renormalization group equation. Okay, and this guy you would call the anomalous dimension, gamma associated to C. The anomalous dimension just tells you how the scaling deviates from the naive expectation that this should be a scalar and should not scale at all. Right? So the result here is then a minus 3 divided by 2, g1 squared, minus a 9/2, g squared, plus a 12 lambda, minus a 14, gs squared, plus a 6 y top squared, if we now include the top contribution to the Higgs as well. So you can see all the psi dependencies drop out, so we really deal with a physical quantity that describes how our system responds under coarse graining. And all of these parameters are rather small, okay? I mean, this RGE flow is not the only source of radiative corrections, but it's one that we can directly include into the event simulation through a running of the associated parameter. So now G1 is tiny, G is tiny, lambda is not too big, and y top can be rather big, okay? But mostly I'm worried about this guy here, okay? Because y top doesn't really run that fast. G1 and lambda do not really run that fast, but GS runs as hell if we go to high PT configurations, okay? So now the beta function of QCD, and that's, it's a bit of jargon. The beta function is not really the anomalous dimension, but it's the anomalous dimension times the coupling itself. So the running of GS is governed by, so if you were to write down dGS by d ln mu, this is a minus 7 gs squared, okay? And the sign here matters if you want to get a Nobel Prize for it, all right? Yeah. So you can see that this is exactly twice the beta function divided by gs. So instead of just normalizing this to lambda squared, this operator, I can sneak in a gs squared here, then I would get an additional plus 2 delta zgs from matching both sides of the 4-point function. If I do this, I add 14 gs squared, and so the dominant part in the anomalous dimension vanishes, or the part that runs fast vanishes. So just by normalizing the Wilson coefficient or this operator with a with a strong coupling here, you absorb most of or some of the radiative effects, not all of them, but some of them you just absorb into a running of the associated Wilson coefficient, okay, by splitting this off. And this is actually what people do, and this is the true reason why when you look at the literature and you look at this operator, then typically it's stressed with the GS squared, okay, because it resumes some dominant logarithmic corrections that you find, okay. So, and that of course has a massive impact if you now look at the PT Higgs spectrum, because that means that this operator gets damped with the running of alpha S instead of staying constant. So if you have to include this to get this deviation in the tails, to get this right a priori. Of course, these guys also relate to finite corrections that you really have to calculate from first principles, so you can't get away with doing renormalization improvements for all of these. So fairly technical, but has its place. Okay. I also picked this operator because it's a special one, because all radiative corrections are proportional to itself. So typically they will mix under RGE flow. So and you can see this by looking at, say, a 4 fermion interaction where you couple up and down and charm and strange, for instance, as you would get from a W exchange. Okay, so if you do now QCD corrections to this, you can color correlate these two lines, okay, or you can color correlate these two lines. And this leads to two different amplitudes in color space. So you see that radiative corrections will generate new structures, and both color structures will mix under RGE flow. So that's one of the reasons why you need a basis, and a basis is by definition minimal in size, because if you are interested, or if you really worry about these precision effects that come about that become relevant when you want to measure Higgs properties as precisely as possible, then these effects matter, and you need to take them into account. Okay, so are there any questions related to that? Yeah? Yeah. Yeah, I mean, this not really. It's just an A function. Just an A0 function. Yeah? So this operator gives you such a diagram. Yeah. Now we just close these. This is really particular to doing radiative corrections in higher dimensional field theory. It's not I mean, we have one operator insertion. So we have to actively veto to calculate this. That you could also, you could write down a diagram that looks like this, right? How do I get, I can get two of these somehow. Can't see this, I'm too close to the blackboard. I think I have it somewhere here. Yeah, like this. Yeah. So this would be a dimension 8 operator. Yeah, like that. Be one loop. So in principle, if you allow in general for these terms, then they create new divergent structures, new 1 over epsilon terms in the Feynman diagrams or in the expressions, which can't always be absorbed into the operator structures that you're dealing with at dimension 6. And this is really where the technical bit of renormalizability comes in. So if you only deal with dimension 4 operators, it's always guaranteed that you are not exciting new operator structures that can't be mapped onto the dimension 4 ones that are already there. And of course, this is where you have to say actively, I'm only interested in dimension 6 interactions. And then you're fine. This is what I mean. It's technically renormalizable, but it's not a renormalizable theory. Yeah?
So there's like a really similar operator to this one with the
cylinder or
Yeah.
Gluon. Is there some obvious way to see why there's no operator mixing between those?
Because one is CP even, one is CP odd. And we don't really have CP violation included in the standard model. There is no mixing at one loop, right? I mean, Michael. So this is your advisor, I suppose, because you know a lot of this. So it's really Copenhagen people. If you're interested in these sorts of things, then you should look up papers by Michael Trott and collaborators. He done a lot of this work, and you find all details that you like to know there. They usually don't really calculate with gauge fixed parameters as I do here, but they use something that is the background field method, where calculations are a little bit easier, okay, especially when you have to worry about operator mixing. Here for us, this is a nice and simple example, so we're not too fussed about this, okay? Any other questions? Everybody hungry? Yeah?
Adding the coupling of the GS, does it change the
No, because GS is just this coupling constant dimension 0, right? I mean, I did this here a little bit, dirty, and that a proper German would have book-kept all the mu dependencies in all the interactions when you go to dimension bigger than 4. But you get the idea, and the final result is gauge independent, and it matches with everything that's there in the literature, so it's correct. All right, and I won't keep you any longer, so thanks for listening to me, thanks for all the nice questions, and I enjoyed this a lot. I hope you had some fun as well. Okay, see you around. Yeah, two things, all right? So I forgot. I'm still around tomorrow, so if you want to talk to me, you can always do that. A second thing, so our noble leader Tillman, together with Sally Dawson and myself, we are writing a Higgs review, big one. And we thought, well, there's 100 pages, okay? So that's, for my standards, that's quite big. So, and people like you are the target audience. So what we want to do is we're going to put that onto the Twiki once it's in a shape that is not, too embarrassing. And I would be super grateful, and I think that extends to Tillman as well, and Sally,